Hello, and welcome to the summary of the first lecture of AI and Machine Learning 2. So, in this lecture, the first chapter of Introduction to Deep Learning, we will cover first the multi-layer perceptron, the activation functions, and the feed-forward process. So, the multi-layer perceptrons form the foundation of many modern deep learning models. They consist of interacted layers of artificial neurons and represents one of the simplest and most widely used neural network architectures. MLPs can be applied to both classification and regression tasks. So, let's move on to the structure of the MLP. First, we have the input layer, which receives datasets features. It has no computation, and its job is only to pass data to the hidden layer or to the next hidden layer. Next, we have the hidden layers, which could have either one or multiple, and they are the layers where the real computation takes place. Finally, we have the output layer, which produces final prediction. Now, let's move to the perceptron. It is a classifier that forms the building block of more complex neural networks. It takes an input vector x and computes a weighted sum of the inputs, which is passed through an activation function to produce an output, where wi are the weights, b is the bias, and f is the activation function. The perceptron can learn linear decision boundaries, making it suitable for linearly separable data. An activation function determines whether a neuron should be activated by transforming the summed input, introducing nonlinearity so the model can learn complex patterns. The bias shifts the activation function, allowing neurons to activate even when the input is zero, improving the model's flexibility and accuracy. It's worth mentioning that, except for the input features and the activation functions, which we choose for each layer in advance, all the weights and biases are trainable parameters, so its initial values are set randomly. Now, as we've mentioned before, activation functions introduce nonlinearity, enabling neural networks to model complex patterns. Their selection is crucial for performance, as each function is suited to specific layers or tasks. Let's start with the first one, which is a sigmoid function. The sigmoid function compresses inputs into the range 0 to 1, making it ideal for binary classification to present probabilities. It is defined as shown, and it maps large negative inputs to values near to 0 and large positive inputs to values near to 1, which leads to its drawback. In deep networks, sigmoid can cause the vanishing gradient problem during backpropagation of the learning process, slowing or halting the learning. We will understand better this issue when we dive further in the training process. Moving to the second one, which is the hyperbolic tangent. It maps inputs to the range between -1 and 1, providing stronger negative and positive responses than sigmoid. It is defined as shown. This symmetric range improves input representation compared to sigmoid, especially in hidden layers where both negative and positive activations add in the learning complex or in learning complex patterns. However, like sigmoid, the hyperbolic tangent can still face the vanishing gradient issue in very deeper networks. Now, moving to the rectified linear unit. This function is the most commonly used function in the deep learning today, due to its simplicity and effectiveness. It is defined as shown, and it outputs the input if positive, otherwise it outputs 0. This addressed the vanishing gradient issue in the sigmoid and hyperbolic tangent, as positive values keep a gradient of 1, enabling faster and more effective training. However, ReLU may encounter the die-in ReLU problem, where neurons get stuck outputting just 0, which means becoming inactive. That problem was addressed by the leaky ReLU, which modifies the standard ReLU function by allowing a small non-zero gradient for negative inputs. This prevents the Dyn ReLU issue by introducing a small slope for negative values. Moving to the next function, which is the softmax function. It is commonly used in the output layer for multi-layer classification problems. It covers raw output scores, or logits, into a probability distribution over multiple classes. The function ensures that the sum of the output probabilities is equal to 1, making it ideal for problems where the output must represent probabilities of mutual exclusive classes, such as in image classification. Now, let's move now to the selection process. The choice of the activation function depends on the layer type, network depth, and a specific problem being solved. Some general guidelines are: first, if we have an output layer for binary classification, sigmoid would be the better choice. If we are in hidden layers in general, ReLU or Licky ReLU are the best choice. If we are in the output layer for a multi-class classification, softmax is the most suitable activation function. And finally, if we have a hidden layer requiring symmetric activation, and we can see that when we learn more about recurrent neural networks, the hyperbolic tangent would be the best choice. And keep in mind that understanding the advantages and the limitations of each activation function allows for better performance tuning of your neural network. Now, the feed-forward process is the first step in training a neural network. Input data passes through each layer from input to output, with each layer applying weights, biases, and an activation function. The computation for each layer is as we've mentioned before. Now, we can make a general for the whole network using the following equations, where ZL is the weighted input to the layer L. WL is a weighted matrix of layer L. A of L minus 1 represents the output activation, or we call it the activated output from the previous layer, or the input data if it's the first layer. BL is the bias vector for each layer, taking into consideration that each neuron in the layer L has its own bias. F is the activation function. Keep in mind that each layer has its own activation function. Now, as for the output of the final layer, AL, where L is the sum or is the number of layers, serves as the model's prediction. So we don't call it the activated output, we call it the model's prediction. For classification problems, this is often a probability distribution over the output classes. Now, the model has finished its first feed-forward process, providing its prediction. The question here, did it learn anything? And the answer is no. So, we need to understand that the feed-forward process generates predictions, but the learning occurs in the back propagation, where the model adjusts weights based on the error between predicted and actual outputs. So what we need now is to compare that predicted value with the actual value, or the true value. And we call that the error, or the loss, where our future goal from the learning would be to minimize this error. And we will cover it in the upcoming videos. So, thank you and see you in the next video.